2 points, lines, and planes. The instructions say use the figure below for exercises 1 through 8. Note that line RN pierces the plane at N, so it's passing through it. See those dotted lines? So R is above the plane. It's not showing a point below it, but that dotted line means it's behind it. So since it pierces it, R is above it. The lines that are on the plane would be these two. Okay, pierces the plane at N. It is not coplanar with V. Plane V, it's not in that plane. All right, so let's look at the answers for the first couple of problems. First is name 2 segments shown in the figure. Now, I, of course, listed a whole lot more segments than necessary, but you can just look at this list. I tried to exhaust the whole list. I mean, I have segment AN, segment NX, segment NM, and NC, and RN, and AX, and MC. So there's a bunch of segments. I named a bunch of them. Plus, I named them both ways. If you say AN, you could have said NA instead. Not that that's 2. That's only one segment. If I say NM, I could have said MN instead. But that's just the same segment. So I've actually listed 1, 2, 3, 4, 5, 6, 7 unique segments, but you could have listed them either way. And they said just 2. So if you did 2, then you're fine. What is the intersection of line CM and line RN? Now you have to know how to read these things. You have to read them correctly. That's line CM, line RN, and of course it's point N. You could put a capital N because that represents a point, or you could write the word point N. Next, name 3 collinear points. 3 collinear points. Listing them, it's point A, point N, point X. That's one set. Point C, point N, point M, point N, point C, or C, point N, and M. That's another set. So all you had to do is list 3. I named 2 different sets. Next, it says, what are 2 other ways to name plane V? There's a lot of ways to name plane V. Any 3 non-collinear points, any 3 points on plane V that are not in a line. For instance, I said plane ANM would work. Plane MNX, that would work. Plane CNX, or CNA, or ANC, either way you name those 3 points. 3 non-collinear points that are on that plane. That'll work. Next, it says, are points RN, M, and X coplanar? All right, we got R is above it, N, M, and X. No, they are non-coplanar. Now, any 3 that are non-collinear here would be coplanar. If you can draw a triangle through 3 points, then they're coplanar. But now what happens, we can draw a triangle through these 3, they would be coplanar. I could even draw a triangle through RN and RM and N. That would make them coplanar, but they're not coplanar with a 4th point X. So nope, R is above the plane, and therefore they're not coplanar. Next, name 2 rays in the figure to the right. So just naming 2 rays shown in the figure. And of course, I put a few, but there are many others starting at N. I could have said ray in A, ray in X, ray in M, ray in C, ray in R. That's starting just at N. There's also rays like AN and ray XN and so on. Make sure you name rays left to right. I looked at some of the work that's already been turned in. People were naming rays the other way. It always go left, right, end point first. Then it says name the pair of opposite rays with endpoint N. There's 2 pair. You could have said ray NA and ray NX, or you could have said ray NM and ray NC. Those are both pairs of opposite rays that have endpoint at N. And then how many lines are shown in the drawing? I can only see 3. Line AX, line MC, and line RN. Those would be the 3 lines in the drawing. All right, down here at the bottom. Now, I've noticed a lot of people are just putting always, sometimes, and never true. You should be able to give a reason. You should know why that it's one of those things. Like the first one says, R rays GH and HG, or ray GH and HG are the same ray. Never. For one, they don't have the same endpoint. They can't be the same ray unless they have the same endpoint and they go on the same line. So same rays must have the same endpoint. Next are ray JI and JL are opposite rays. They could be. They do have the same endpoint. We just don't know if I and L are in opposite directions on the same line. See, If J, I, and L are collinear with J between I and L, then that would be opposite rays, but we don't know. So we have to say sometimes. We're not sure about that one. Next, number 11, a plane contains only 3 points. Never. Planes can't contain infinite number of points. They have to have at least 3 non-collinear points, and if you have 3 non-collinear points, you have exactly one plane, but a plane is going to have an infinite number of points on it. Next, number 12. 3 non-collinear points are contained in only one plane, always. That's our postulate. 3 non-collinear points are contained in only one, just one. One and only one plane can contain the same 3 non-collinear points. All right, number 13, if line EG lies in plane X, then point G lies in plane X. That's also an always. If the line is in the plane, then any point on that line would be in the plane. So if the line is in the plane, then all points of the line are in the plane. So that would be an always answer. Next, with number 14, if 3 points are coplanar, they are collinear. They could be, sometimes. See, it takes 3 non-collinear points to make a plane. So what 3 points are we talking about? They just said 3 points. It could be the 3 non-collinear points that determine the plane. Or we could have 3 points on a plane that are collinear. So when so many points, what 3 are we talking about? You know, it could be 3 non-collinears, it could be 3 collinear, so that's why it's sometimes. Number 15 says, is it possible for one ray to be shorter in length than another? No, rays doesn't have length. All rays are infinite in length. They have a beginning and then they keep going. They keep going, they don't stop. So no, all rays have an infinite length, so there would not be one longer than the other. Next, number 16, open-ended. You were to draw a figure of 2 planes that intersect in line ST. So I drew a planes N, and I called this one plane M, and they intersect. That's where they meet, and I call that line ST. So line ST is their intersection. So that was open-ended. You were just supposed to draw a picture, and that's what mine looked like. Okay, over on the next page. Again, we're doing some drawings. Your picture may not look exactly like mine. It says, draw a figure to fit each description. Through any 2 points, there is exactly one line. So I have 2 points, A and B, and I drew a line connecting them. And of course, that would be line AB. Now that I have those points, I could call it line AB if I'd like. B, 2 distinct lines can intersect in only one point. Here I have line M and line L intersecting at point P. And that both of these are 2 of our postulates in the book. Okay, so it should have been really easy to illustrate them. And of course, in the book, they had illustrations by those postulates. You could have used those. Number 18, reasoning. Point F lies on ray EG. Point M lies on ray EN. If F, E, and M are collinear, what must be true of these rays? Now notice they both have the same endpoint, so it's possible they're opposite rays. Well, that is what it is. The rays are opposite. They're the same or they're opposite, because I have EG, and I'm drawing EG going in that direction, okay? And of course, EG going in that direction says F lies on EG, so F could be out here. That's a possibility. And it said M lies on EN. Well, I drew EN going in this direction, right? And then I, of course, put M on ray EN. So see, this is a set of opposite rays that have those. If F, E, and M, and of course I have F, E, and M are collinear, what must be true about the rays? Here I drew them where they were opposite, but they could have been the same. We could have drawn, I didn't draw a possibility of that. We could have had EN going in the same direction that EG did. We could have had all these. E could have been like on a line, and all of these other points, N, M, G, and F could have been on one side of point E on that line, and then they would have been the same ray in that case. Number 19 says, what other terms or phrases mean the same as a postulate? Well, a postulate is a statement accepted to be true without proof. An axiom is the other word that they use in the book. Next, number 20, how many segments can be named from the figure at the right. So what I did, I named all the segments. There's 6 unique segments. And starting at D, I said there's DE, DF, DG. All those are unique segments, but then they also could have been named ED, FD, and GD. See, I listed those segments, and then I listed them the other way, just turning the letters around, but it's still just 6 unique segments. Then I named the ones with E as one of the endpoints. I've already named ED, so I'll just go EF and EG. So EF and EG, and if I flip them around, FE and GE would be the same segments. And the only segment that's left then is FG or GF. So you see, understand what I did. I started here naming the segments, then I never went back in that direction. So I started here, named all these segments, then I started here, named the 2 segments that they had as endpoints, then I started here and named that segment because it only had one other segment left. So there were 6. Next, it says use the figure at the right for exercise 21 through 29. Name the intersection of each pair of planes or lines. Okay, this looks like these are trapezoids on the end, so it's a trapezoidal prism. It looks like some sort of a trough or a gutter or something, but still, each of the faces, and there's 6 faces, the top, the bottom, the left, the right, and the front and the back. 6 faces there, but of course we know that there's other could possibly be other planes and things in there as well. They start us off, number 21, plane A, BP, which is this end here of the figure, and BCD is the top. They intersect at line AB. So the back and the top intersect in line AB, and you must say line. Don't put segment, don't put points. If you just put capital letters there, then it would be wrong. You have to say line. Next, we have 2 lines. Where do these 2 lines intersect? Line RQ and line RO at point R. Of course, it should be obvious because R is in both of the names. And 2 lines can only intersect in one point, so if R is on both lines, that's got to be the intersection point. 23, planes ADR and DCQ, where do they intersect? They intersect in DR. ADR is the left side of this figure. DCQ is this end of the figure, so they intersect in line DR right here, DR. So this side and that side intersect in line DR. Next, planes BCD, which is the top, and BCQ, which is the right side, over here on the right side. Where do they intersect? Line BC. Line BC is where they're going to intersect. The top and the right side intersect in line BC. Make sure you name it as a line. 25, we have 2 lines. Again, line OP and line QP. They have to intersect at P because P is in the name of each of them. And again, you can look at the picture. OP is this one, going that way. QP is this line here. And they do cross or meet or intersect at point P. That's the point they have in common. The intersection is the points that 2 geometric figures have in common. Number 26 through 29, name 2 planes that intersect in the given line. So they start us off with a line RO. RO is that bottom corner of this trough here. The 2 planes will be ADRO, which is the left side, and then the bottom, which I called PQRO. Now, all we really have to do to name planes, as they did up here, is just name 3 points. But when we have a figure like this, sometimes it's better just to do all 4. That way, everybody has a similar answer. You may have them in a different order, the points, but you'll be able to tell that your answer is the same as mine if you list all 4. Okay. For CQ, CQ is this line here, so it's the front of this trough here and the right side. So I called them the right side BCQP, and then the front here I called DCQR. That's the way I named them. Name going around them, name all 4 points. You could have started here and said RDCQ, but still go around it, okay? Do not skip around and do stuff like DQCR. Don't name them that way because we need to go around the figure, name the planes. Next, the line DA, what planes intersect to at line DA, the top of the box. The top of the box, I called it BCD A. I probably should have called it A, B, C, D since that was alphabetical, but I didn't. And then, of course, the left side of the box here, which I called O-R-D-A. O-R-D-A. And again, your name might be a little different to name that one. Then number 29, line BP. Line BP, that's back here in the back. So the back of the box, which would be ABPO, ABPO, and the right side, which I called CBPQ. Okay, so those are the planes that intersect to form those lines. Now the next one's looking at some of your work, you would have to use graph paper. It says coordinate geometry. And if you turn in your homework online and you don't include your scratch paper, then you're not getting credit for these. I've already told you this is an honors class. If they ask you for a sometimes, always, never, a yes, no, true, false, or collinear, non-collinear, then you have to show me why. You have to prove. You don't know if these are collinear or not until you graph them. Sorry, that was the bell. You wouldn't know until you graph them. So I graphed each one, and I'll show you my graphs real quick for number 30. Number 30, zoom out just a little bit. Number 30 looks like this. These are my 3 points. Yes, they were collinear. I can draw a line connecting those three. 31, yes, they were collinear. They were all on the x-axis when I graphed those. Notice all of them had 0 for their y coordinate, so they didn't go up or down. They just went out on the x-axis. For number 32, they're non-collinear. Now, it almost looks like you could connect them, but you can't. You can look at this, and remember, you've had algebra, so if you think about going from here to here, the slope would be down 1 over 2. And, of course, if you reverse that, go over 2 and up 1, over 2 and up 1, see, we go just beneath that point, so they're not collinear. By the naked eye, they may look like it if you just look at it, but if you put a ruler on there, they're not in the same line. 33, it's a little more obvious with the graph. They're not collinear. These are the 3 points. They're not collinear in that picture. Number 34. 34, yes, they're all, well, they're collinear because they're all wrong. Mr. Stevenson graphed them all wrong. 0, 4 would be here. 2, wait a minute. Oh, let me look at those. Yeah, I made a mistake. 0, 4 is there. -2, 0 is, let me talk about these points again. -2, 0, that's right. 0, 4 is wrong. I should have went up 4, not there. It should have been 0, didn't go anywhere left or right, and went up 4. So this one was wrong. So you found out real early that Mr. Stevenson makes mistakes. And then the other one is 2, 0, and why it's all the way out there. It should have been here. I must have graphed those points and then tried to label them afterwards, and then, of course, graphed one of them wrong. So I just really messed that one up. So that's what it would look like, and definitely they're non-collinear. Non-collinear. Big mistake, Mr. Stevenson. All right, but anyway, there's the 3 points, and they're non-collinear. And let me check this last one just to make sure. It says -4, -1, that's right. -1, -2, that's right. And 2, -3, that's right. And again, I can put a ruler on that. They are collinear, but I can just think of how do I get from this one to this one using rise over run. I went down and over 3. I went down and over 3. So definitely they have to be collinear because they have the same slope. It's sloping downward like that, and y'all have had algebra, so you should know a little bit about slope. Okay, that's all the homework problems for 1-2, points, lines, and planes. Make sure you make corrections to your homework because when it goes in the notebook, it has to be correct. And if I were to ask you to do one of these on a notebook test and you didn't have the graph, then you wouldn't have what it took to get the full credit. So make sure you go back and do those graphs if you didn't do them.